Okay, close everything up for a second. Let's take just like 5 minutes. Let's finish up what we started yesterday. So, solving a perfectly elastic collision, solving for the results of a perfectly elastic collision. So, Seth, close it up for a sec. So we got this one down, and then we'll get back to that stuff. All right. So what did we say? If it's perfectly elastic, that tells us that what's conserved. Momentum is always conserved in any collision. Kinetic energy is also conserved, right? So then we know that if we have a 8 kilogram ball traveling initially in the positive x direction at 8 meters per second, and it ends up with a velocity of 2 meters per second in the positive x direction, right? The 6 kilogram ball is initially, wasn't it at rest? No, we don't know, okay? We don't know anything about the 6 kilogram ball, but we want to know what was its velocity prior to the collision. Okay, does not seem like enough information, but it is, right? So if we look, remember we just said equation 1 is the equation we get from conservation of momentum. So in this case, the v's, we have to attach a sign to these because they're acting like vectors, right? And so we ended up with mass times velocity of object A plus mass times velocity of object B before the collision must equal mass times velocity of object A after the collision plus mass times velocity of B after the collision, right? And we're actually trying to solve for V2, aren't we? Right? We want the velocity of object B for object 2 prior to the collision. Right, and that was asking for, yeah, prior to the collision. Okay, so there's one equation, but notice we've got two unknowns in this, right? So we need another equation. Well, here it is. We get the log conserved, or we know that kinetic energy is conserved. So 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals 1/2 m1 v2 prime squared, v1 prime squared, plus 1/2 m2 v2 prime squared. Okay, now what does it mean when you square? Now remember, in kinetic energy, it's a scalar quantity. It doesn't depend on the sign of the velocity, right? All we're looking at is a magnitude, it's a speed, okay? Just ponder this for a second. How can you, and this is a pretty sophisticated question, but I want you just to think about this, and you may come back to it later in your mind, but how can we combine two equations in a system, one of which involves a vector and one of which involves a scalar? Okay, that seems a little weird. Okay, if it doesn't to you, that's a red flag. If it doesn't to you right now, it's a red flag that'll pop up later. Okay. So normally, if we were trying to deal with a vector and we wanted to break that up into components or something, right, we'd have to have both an angle and a magnitude to take care of both the magnitude and the direction, right? Does that make sense? Okay. But in this case, because we're talking about a one-dimensional collision, we don't need the angle, right? So when we talk about a vector, a one-dimensional vector, what does that mean? If it's moving in this direction, what can you tell me about? It's positive. That's it. That's all we need to know. It's moving in that direction. It's negative. Okay? Still, it's a vector, so we have that extra bit of information, whereas in this equation here, it's a scalar, right? It shouldn't matter. All we're ever looking about, so as far as the speed is concerned, if it's moving in that direction, the speed is positive. If we're moving in that direction, the speed is positive, right? Because it's a magnitude. Does everybody get that? Okay, why? How can we do this? Notice the squared. Right? What's that going to do? It's going to make it positive, isn't it? Physics gods are pretty wise, right? Everything is foolproof here, right? We know that these equations are based on basic principles, so they have to always work, right? They do, right? They do, because in a one-dimensional collision, if it's negative, it doesn't matter. You square a negative, you get a positive, right? Everybody get that? Okay, so it does work out. So we end up then with these two equations, and what do we find then? So if we simplify all the coefficients, they just boil down to these two equations, right? The vector nature of this just means that it could be negative, right? We could do this if we wanted to then, because if it's negative, it's getting squared, which makes it positive, right? So really when we're solving for V2 and V2 prime, we're solving for the vector values of that. There's going to be a sign attached to them, okay? But because we're squaring them, who cares? We know it's going to be positive. Square is always positive, right, for real numbers. So then all we have to do is solve this system. Now that's not a hard system to solve. You could solve that system. That's just a linear quadratic system. You did that in Algebra 2, right? All you do is just solve by substitution. But let's go ahead and cheat a little bit. Let's just use Desmos. All right, so in Desmos, if I okay, I'm just going to let's call V2 x and V2 prime y, just to make it easier, so we can use the coordinate axes. So then if I just type in the equation 64 plus 6x equals 16 plus 6y, look what I get, right? I just get a line. Okay, makes sense. Equation 2, 256 plus 3x squared, agreed, equals 16 plus 3y squared. Okay, and what I get in that case is a hyperbola, right? Where are the intersections of this thing? Notice there's only one intersection, and the intersection occurs right there. So what's that tell us?
Your initial speed and your final speed.
Initial velocity. Velocity for object 2 is 1 meter per second, and the final velocity is 9 meters per second. Let's just see if that makes sense. You know, you always want to look at stuff in physics and say, does that seem reasonable, right? So in the context of the problem, then, we know our solution is, let's write down those solutions. So we get V2 equals 1 meters per second. V2 prime equals 9 meters per second. Okay, look at the original problem. Let's see if that makes sense. So if the 8 kilogram ball is coming in with a velocity of 8 meters per second, and it's leaving with a velocity in the x direction of only 2 meters per second, right? What has to be happening between the ball 1 and ball 2?
Transfers.
It has to transfer some momentum, some positive momentum to ball 2, doesn't it? Right? Because it's leaving with less. Okay, furthermore, it has to transfer some energy to ball 2, right? So ball 2 is going to come out with the most energy, and for sure it's going to get most of the momentum in the x direction. So doesn't it stand to reason then that for ball 2, it's both its speed and its x component of velocity would have to increase, right? That's reasonable, isn't it? Right? Everybody see that? Okay. All right, how could you? Okay, I'm going to throw a real tough one at you here. I'm not going to make you, well, I don't know, maybe I will.
Okay.
But I, at the very least, I want you to That's wrong, by the way, so don't go by those numbers. This is a very hard college level problem. Okay, so don't, I mean, this is pretty challenging.
Wait, is it assuming that it's perfectly elastic?
Perfect, yeah, we have to assume it's perfectly elastic or we can't do it. Okay? Right, if we don't know how much energy is lost, we're sunk. I mean, they'd have to give us either a percentage of the energy loss or we'll assume it's perfectly elastic. Right. So, okay, so this is pretty hard, right? We got a blue bumper car traveling. They tell us the direction it's traveling and the speed it's traveling. So we know its initial velocity vector, right? Or momentum vector. It bumps into a stationary red bumper car. We know the mass. The blue car bounces from the collision. They give us the direction and the speed. Okay, and we're supposed to know after the collision along what trajectory. So what is the vector? What is the final velocity of the red bumper car? Okay. So how could we do this?
Are we going to break it up into
Components?
yeah.
Okay, so the momentum, right, momentum is a vector quantity, so we would have to use a table, right? We'd have to set the initial, we know that momentum is conserved, and so the initial x component of the momentum of the system, of both cars combined, would have to equal the final x component of the momentum of the system, both cars combined. Fortunately, the red car is initially at rest, so it contributes nothing to the momentum, right? Okay, so that part's looking pretty hard. Now, here's my question, at least my first question. My question for today, and we'll put the rest of this on hold. So if we just wanted to know the speed of the car, is that going to be a hard or an easy problem to answer?
The speed should be fairly easy.
It's going to be a lot easier, right? Because the speed can be determined just by conservation of energy, right? And so do you guys see right now that if we know, we could easily calculate the initial kinetic energy of the blue car and the system, therefore, because the red car has no kinetic energy, right? Everybody see that? We know its mass and we know its speed. Direction's unimportant, right? Because energy, and this gives you some idea about how useful energy is because it's a scalar quantity. It's a lot easier to deal with, isn't it? Right? We know the final kinetic energy of the car based on its final speed, and the mass didn't change, right? Well, if this is a perfectly elastic collision, what can you tell me about the kinetic energy of the red car after the collision?
It's got to equal whatever the blue car lost.
Whatever the blue car lost, doesn't it, right? Because we know initial blue kinetic energy, red 0 initially, right, equals final blue kinetic energy plus final red kinetic energy, right? So that's easy. We can set this up then as the red. I can color code this up. So the red final kinetic energy is just going to be equal to some blue number, right? Blue initial minus blue final kinetic energy. It can be some positive number. It has to be, right? What do I have to do to solve for V? Well, I know red M, right? So I just divide each side through by 1/2 red M and square root it, and I know the speed. That's easy, right? That makes sense? And if I knew the speed of the red car afterwards, things aren't quite as daunting then, right? Then all I've got to do is just figure out what's the direction, okay? And we ought to be able to do that from our table. Does that make sense? Give you a little inkling of how you could approach that. I'm not so worried so much about being able to do the problem. I just want you to kind of how you think about this, how can you think about this like a physicist? You want to see what, you want to use the law of, or you want to use the conservation of kinetic energy here, because it's an elastic collision, to find the speed, and that makes this problem a lot easier, okay? All right, we lost a bunch. I don't want to do any more of this with this and that many people, so I'll let you guys work on stuff. The other side, by the way, assignment number 2 is back up. I replaced that problem with the one that was supposed to be on there.